Hello. So we're going to talk more about binomial models. I'm going to give you some more examples and some problems where we're dealing with numbers that are really, really big and kind of how we can use the calculator as a shortcut for that. So we're going to go straight into an example. So this example, it says a small airline overbooks flights on the assumption that several passengers will not show up. Suppose that the probability that a random passenger shows up is 0.92. For a particular flight, 22 tickets are sold. However, the plane only has 20 seats. So one thing that's always good to do when you know you're dealing with a binomial is to think, well, again, first, a binomial is when you know the probability of something happening once, or just kind of the general overall probability of something happening, and you are trying to find the probability that it happens a certain number of times. That is when we're dealing with binomial. So in this binomial model, the probability that a random passenger shows up is 0.92, and we're going to assume that that's independent and that it stays pretty much true all the time. And then 22 tickets are sold, which means technically in this problem, my sample size n is 22, or my trial size. We're doing 22 trials, and for those 22 tickets, each passenger may show up or not show up. So first example, or first question says, what is the probability that exactly 20 people show up? So we want to know for the 22 that are sold, the 22 possible trials, we want to know the probability that exactly 20 will have success, which is that they show up. So again, we recognize this is binomial because we know the probability of something happening once, and we want to know the probability that it happens a certain number of times. N is 22, and P, our probability of success, is 0.92, where X is defined as the number of passengers who show up out of 22. So if we want to know the probability that exactly 20 show up, we're finding the probability that X, that thing we defined, is equal to 20. When we use our formula for this, right, our formula says N choose X, so 22 total, choose 20. Probability of success to the X, so 0.92 to the 20, 20 show up, times probability of failure to the N minus X. So 0.08 is probability that someone doesn't show up, and that would happen for two people. So 20 showed up, 22 didn't. So to actually calculate that, we could, again, use the actual formula. We could do 22 choose 20 in our calculator, and then times 0.92 to the 20 times 0.08 to the 2. But this is where we can use our shortcut, so to speak. This would be a binom PDF because we're finding the probability of X equaling a certain individual number. So I'm going to do second vars, go up to binom PDF, which is A. Trials is 22, P is 0.92, and X value, what I want it to equal, oops, I erased the 0.92 accidentally. And then the X value, we want it to equal exactly 20, and then paste, it looks like that. And we push enter, and that is our answer, 0.2789 or 90 if we round it up. One thing I wanted to note is that writing what we saw in the calculator just now, writing binom PDF 22, 0.92, 20 is appropriate as your work, so to speak, on a free response question. You can use that calculator speak as your work as long as you've defined your binomial model and the random variable X somewhere in your answer. So this thing that we did up here where I said binom 22.92, X is the number of passengers who show up out of 22, that right there is defining the binomial model and defining the variable that you're dealing with. You would need to do that up here in order to use this binom PDF 22.9220 as your work for this problem. Otherwise, you have to show the formula, right? So that's kind of the piece there in terms of AP exam, what you get credit for. You're not going to get full credit if you don't show your work. So just keep that in mind. And if you just put a number, if you just put 0.2790 without anything else, you not get any credit at all. So keep that in mind. All right, so let's look at a part B where we are talking about slightly different questions. So this one says, what's the probability that the airline will be able to seat all the passengers who arrive? Right, just that everyone who shows up has a seat. Well, if 20 people show up, they have 20 seats, they'll be able to seat everybody. But if 19 people show up, they will still be able to seat everybody. If 18 people show up, everybody has a seat. So 20 or less people showing up is when they will be able to seat everybody who arrives. So what we're finding here is the probability that 20 or fewer passengers show up. So again, we define our binomial. If we already did that in part A, we don't have to do it again, but there it is. We're finding the probability that x is less than or equal to 20. So again, formula-wise, I would show all of the formulas for 20, 19, 18, 17, 16, all the way down to 0. You can do a little first and last with a little dot, dot, dot in the middle, and that works. But we are doing this one as a binom CDF. So again, binom CDF is cumulative. That means everything up to and including a certain value. So I would do second vars. Oops, I'm having trouble. Clear. Second vars, and then binom CDF. Again, we still have 22 trials. P is still 0.92. I'm still going to put 20 as the x value, but now because we're using this binom CDF function, it's going to do 20, 19, 18, 17, 16, all the way down to 0. Add all of those together because I did it as binom CDF. And there is my answer. Again, right, we can use this as work, binom CDF, blah, 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 as your work, as long as somewhere, even if it's up in part A, you defined the binomial model and defined your random variable x as the number of passengers who show up at 22. Otherwise, we would need to show this work. Again, that's starting at 0 because we wanted less than or equal to 0. There's a formula for 0. There's a formula for 1 plus dot, 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 all the way up to the formula for 20. Starting at 0, ending at 20 because we wanted less than or equal to 20. So that would be the work that you would have to show in order to get full credit. You can write binom CDF, you can write that calculator speak as your work as long as you've defined things up here. And so I'm giving you options, just keep that in mind. So then if I had a part C, which says what's the probability that the flight will be oversold? Right? Oversold means that more people show up than they have seats for. So in this case, that would mean if 21 or more passengers show up, then somebody will not have a seat, and then they will have to figure that out. So we're finding the probability that x is greater than or equal to 20. Right? Formula-wise, that's basically 21 people show up. So there's our formula for 21. 22 people total, 21 show up, 0.92 to the 21, 0.08 to the 1. 21 show up, 1 didn't. And then plus the formula for 22. It's greater than or equal to 21. If there's 22 total, it'd be 21 or 22. So there's the formula for 22. Right? So I could do this the long way in my calculator using the actual formula. 22 choose 21 times this, times that, etc. But if I want to be able to use my shortcut, the binom PDF, binom CDF stuff, I'm in a little bit of a stuck place. And the reason for that is our calculator has a shortcut for exactly. So if I go to second vars, I have binom PDF, which would give me exactly 21 probability. What's the probability that exactly 21 show up or exactly 22 show up? Binom CDF tells me everything up to and including. So binom CDF is only doing a probability for less than or equal to a certain amount. There is no calculator shortcut for greater than or equal to. There's just not. TI didn't think of one. They didn't put it in there. They didn't feel like it was important. So if we want to use our shortcuts, we have to work backwards. In other words, if I can think about, well, I want 21 or more, so what do I not want? What part of that probability do I not want? So if I want my answer to include 21 or more, what I don't want is 20 or less, right? Think about it as we have individual whole numbers. Think about what you do want, and then what do you not want. The reason that's helpful is if I do binom CDF for 20 or less, which I already did in the last problem, right? That's the probability that 20 or less show up. All I need to do now is do 1 minus that number, right? Remember that for all probabilities, for all of the options for that variable, the probability should add up to 1, right? So if I find the probability of what I don't want to happen, I can do 1 minus that, and that will give me the probability of what I do want to happen. Right? So in other words, I'm doing, again, I could do binom PDF for 21 plus 22 and get an answer, or I could find that binom CDF for what I don't want, which is 20 or less, and then do 1 minus that. Right? Either way, I end up with about 0.46. Again, if I did Binom PDF for both 21 and 22, so if I did 22, 0.92, 21, plus Binom PDF for 22, just change X value to 22, right? And add those together, I get the same answer. So it doesn't matter on this one which way you do it. But I wanted to mention that kind of working backwards trick because there are going to be problems where doing it with Binom PDF repeatedly all the way up is going to be really, really ridiculous. So let's look at an example like that. So this one says, suppose the Texas Red Cross anticipates the need for at least 1,850 units of O-negative blood. It estimates that it will collect blood from 32,000 donors. So for 32,000 people, they could either be O-negative or not O-negative. So our sample size, our trial size, is 32,000 because we have 32,000 chances to have success or failure. 6% of the adult population has type O negative blood, so that is our probability of success, P. We're going to find the probability that they will meet their need. Well, meeting their need means they get at least 850 units or more of O negative blood. So again, our binomial is set up with N as 32,000, P is 0.06. X is defined as the number of donors who have O negative blood out of the 32,000. So the probability I'm finding is that X, the number of donors who have O negative blood, is greater than or equal to 1850. So again, I could work up, start at 1850, and then just do Binom PDF for 1850, 1851, 1852, 1853, all the way up to 32,000. But that would take a very, very long time. My calculator shortcut of Binom PDF is no longer really a shortcut. It's not helping to figure out that probability using that method. So this is where I would want to, so this is me showing the formula part of starting at 1850 and going all the way to 32,000. But this is where I'd want to use the work backwards trick, right? So this is where I want to think, okay, if I figure out what I don't want, so if I want 1850 or more, then I don't want 1849 or less. 1849 or less means they don't meet their need. So if I find that probability and then do 1 minus that, I'm left with what I do want. So that's what I'm going to do. I'm going to go to Binom CDF to figure out what I don't want. So Binom CDF, there's 32,000 people. That's our trials. P is 0.06, probability of O negative blood. And we're going to find X value of 1849 because that would tell us the probability of 1849 or less. In other words, the probability that they do not meet their need, 0.0479. And then if I do 1 minus that, I'm left with what would be 1850 or more, so 0.9521. Okay, so what that looks like on, there's my answer. Again, work on a free response question. As long as you have defined your binomial model up here and written out in words what X is equal to in this problem, that's what I did in these top 2 lines, then you can use this calculator speak as your work. If you don't define those things, you would need to show this formula right here that I did in the middle part. That would have to be shown in order to get full credit for the answer. So even if you get the right answer, you have to have some sort of showing your work. This is showing the grader that you know what type of model it is, that you know what numbers go where, that you know why the formula works the way that it works or why the shortcut works the way that it works. So make sure you are doing that. All right, so there is that example. I'm going to throw one last example up here. I'm not going to go through it in this video. We'll go through it in class next time for those of you that want that extra practice. But it says, according to the internet, 60% of US adults gave up on their New Year's resolutions within a week. For 50 randomly selected adults, what's the probability that less than half of them gave up on their resolutions? And then more than 40 of them gave up on their resolutions. So I'm going to give you a chance to kind of do that on your own, see if you can figure out the answer, and then we're going to go over it in class next time. All right, see y'all later.